Hello everyone, this is Professor Keene. We have been talking about Chapter 2 in a student's guide to the great physics texts titled The Life and Death of a Magnet. In the previous lecture, we talked about what would happen if you cut a bar magnet in half, and one of the main points we arrived at was when you do so, you generate a new north and south pole. So if you have a north and south pole of a magnet, you cut the magnet in half, you don't hold the north pole in one hand and the south pole in the other hand. Rather, your right hand, holding one half of the magnet, has a north and a south pole in it, and your left hand has a north and a south pole in it as well. That brought us up to about this page, and in this diagram in figure 2.2, Gilbert talks about how if you cut a magnet in half, it can be rejoined in the same way that the place that you cut it by aligning the ends correctly so that a north attaches to a south. And he uses the analogy with grafting of a plant. If you cut a plant and then you try to regraft it back together, it will work as long as you graft it in the correct orientation. That's the way that he explains it in figure 2.2. All right, and that brings us up to his chapter 7. So let's spend a few minutes talking about the action of magnets and how it is not merely attractive or repulsive, but is in fact directive. Okay, and that's what he's talking about down here on the bottom of page 21. Let's go to one of the diagrams to see what he means when he says that it's not merely attractive or repulsive, but directive. Okay, so he imagines a terrella right here. So in figure 2.3, you might imagine G and D to be the north and south poles of this spherical magnet. And he's talking about what happens if you were to place a small iron needle near that terrella. Which way would it point? And he mentions that if you put one of these iron needles very close to one of the poles, let's say this point right here, and let's suppose this is, just for the sake of argument, this is a north pole over here. So you've got a north pole on this end and a south pole right here. What happens if you place an iron needle right there? Of course, this side of the iron needle will become a north and this side will become a south, and it points straight out away from it. And this, you might think about this as a lump of clay or something. So you stick it in there, it points straight out. What happens if you put the iron needle at various locations around it? Well, you'll see at different latitudes. So if we think about this as the equator of the magnet, then at different latitudes, if you place these iron needles, they will point in different orientations. Until if you place it right here at the equator, it will be facing horizontally. And by horizontally, we mean in the plane of the horizon. Think about the Earth. If you were standing on the equator of the Earth, this line right here would be the horizon, and that iron needle would be pointing horizontally. And it would not even be bound very tightly. Okay, and he's going to get to that in a moment. All right, but the main point he's making here is sometimes you think of magnetism as simply attractive or repulsive. That is, the south pole of a magnet is attracted to the north pole of another magnet. And that is certainly true, but it's more than that. It tries to orient things in a specific way. Okay, and he also tries to emphasize this when he says, let's suppose you were to take a clump of iron and bring it near one of these terrellas. And let's suppose this is a clump of iron right here. If you put a chunk of iron right here at the south pole of this terrella, it will stick very readily. And in fact, if you take a pound piece of iron and stick it to it, it will stick tightly so that it's hard to get it away. In fact, it might hold it up. If you let go of it, it would stick to it. But on the other hand, if you take a piece of iron and you try to stick it to the side, it is going to stick very lightly. So it would slide off quite easily unless you had that piece of iron being only like 1 or 2 ounces. So he says that a lump of great weight can be stuck to the high latitudes, I guess near the poles, but only iron lumps of very low weight will stick near the low latitudes or near the equator. That's the point that he's making here in chapter 7. Okay, let's go on to chapter 8 of disagreement between pieces of iron on the same pole of a lodestone, how they may come together and be conjoined. What is he talking about here? He's saying, what happens if you were to take 2 small rods of iron, let's say about 2 or 3 finger breadths long, and you were to put both of those rods of iron attached side by side to the pole of a Torella. So look at figure 2.4 here. You might imagine that this point C on the Torella happens to be a north pole of this Torella or spherical lodestone. And let's suppose you take two pieces of iron side by side and you touch them right there. Well, if this is a north pole of the lodestone, these two ends will be south poles, but notice that these two ends right here will be north poles. They acquire verticity, of course. They become north poles of these iron. C, remember, was a north pole. So what happens, what's the point he's trying to make, is that the ends of them will not be joined to one another, rather they'll separate. Why is that? Because those two north poles are going to want to repel one another, and so they will tip away from each other. Okay, that happens if the iron pieces are rather long, say 2 or 3 finger breadths long. What happens then if you try to hold them together? Let's suppose you were to take those points A and B and squeeze them tightly together with your finger. He mentions that once they do that, they can become a single or act as a single iron pin. That is, they will stick together, he says, as if they were friends. So somehow this repulsion can be overcome if you hold them together tightly for a moment, then they'll stick. But on the other hand, if those are very short pieces of iron, say like as long as a piece of rice, then they angle away from each other as shown in figure 2.4, and even if you try to stick them together, they will not. They'll quickly repel one another. He doesn't go into the reason for that, but he's simply noting some experimental observations. He also mentions that in figure B, figure 2.4b, if you take a couple of pieces of iron, suspend them side by side from a string, and bring them near the north pole, let's say, of a Torella, what will happen is they will repel each other. Of course, that is because they're in the vicinity of the Torella. They're acquiring verticity. So if point C is a north pole, points A and B there will become south poles, and they will repel one another. So if this right here is a north pole, I'll color it red, then these will become north poles up here. These will become south poles down there, and they will repel one another. So he's going through these experiments to kind of show us what happens with magnets. Okay. Let's talk about chapter 9. What is he talking about in chapter 9? Well, he's giving a summary of the directions that a compass needle, or he calls it a versorium, will be oriented when placed at various locations around a Torella. So let's suppose we have a Torella in figure 2.5a, and point A and B are the north and south poles of this Torella. And let's suppose you have a magnetized compass needle, a versorium, and you bring it near it. Well, he's showing the orientation that it will acquire. So right here, near the equator of the Torella, it will point in the horizontal or along the horizon of the globe. If you place this versorium right here, then it will point toward the pole. If you put it over here, it'll point away from the pole. Okay, and then here he gives kind of a summary of the directionality of the versoria as you put them near the lodestone. Now this raises an interesting question. What is the direction that a compass needle will point if you place it within a lodestone? This simply maps out what will happen when you place it in the vicinity around a lodestone, but what happens when you place it within one of these Torella? And that is what he's going to show in the next figure. So let's jump to the next page. Here is a picture of the lodestone in figure 2.6. You'll see that he has these versoria placed near the poles right here. At this point, it's pointing in. At this point, it's pointing out. And he says over here, if you break the lodestone in half, it will point in a direction like this, inside of the lodestone. Now, that might seem obvious. Let's suppose that, for example, this end right here is the north end of this lodestone, and this end was the south end. As we mentioned before, when you break this lodestone in half, what happens is you get a south end right here and a north end right here. So if these compass needles, let's suppose this is the north end of the compass needle, so that the south end points toward the north, then if you place a compass needle in here, the south end, the north end is here, it will be attracted to the south end right there, and the south end will be attracted to the north end. Likewise here, I'll keep marking the north ends right here. And maybe I should put, well, I'll just leave it like that, okay? And this might seem obvious until you think a little bit more carefully about what happens in this vicinity out here. And I'd just like to highlight that this is a little bit counterintuitive. So a compass needle will point outward here. I'll draw a few more compass needles. They'll point in that direction and in that direction, as he mentioned in the previous diagram. And then here it will point in that direction. Here it will point in that direction. Here it will point in this direction. Here it will point in this direction. Here in this direction. Here in this direction. Here in this direction along the horizon. Here in this direction. And here in this direction. Okay. Now what I want to highlight is that this is kind of peculiar what's going on in here, because after all, outside of the terrella, this versorium will be pointing to the left in the diagram. But the moment you get inside of the terrella, it's pointing to the right. So at some point it goes from pointing leftward to pointing rightward. There's a flip. If you were to take this compass needle and move it downward, up here it would be pointing to the left, and the moment you get inside of it, it points to the right. That's a little bit strange. So let's think a little bit more carefully about why this happens. And in order to do so, I'm going to introduce an anachronistic idea, something out of Faraday's theory of magnetism that we will not come across until the 1800s with the work of Michael Faraday. So let me draw a picture of a lodestone, like what Gilbert does. And let's suppose we have a north end. This is very blown up. This is very blown up, so let me change the size of my pen for a moment. It's north and south. And we mentioned that the compass needles will point in these directions when on the outside of the lodestone, away from the South Pole, horizontally there, then into the North Pole here. Then, if you break this in half, so that this is a north end, this is a south end, this is a north end, this is a south end, once again, the compass needles will point toward the north, like this. So I'm imagining surrounding this broken lodestone with compass needles. Like this. And the interesting point is right in here, because at some point as you move them in, they will flip and aim in this direction. So this is a little bit peculiar until we come across the idea of the magnetic field. So the magnetic field, the concept of the magnetic field, was introduced to great controversy, by the way, and we'll come across this later on in this course, by a man named Michael Faraday in about the mid-1800s, 1840s, 30s or so, 30 to 50. And I know you're used to hearing about magnetic fields, but just keep in mind how odd of a concept this is. A magnetic field purportedly is something that fills the space around a magnet that we cannot see. Okay? And here's the main idea that Faraday had, or at least the relevant idea for our discussion. Magnetic fields, and this is the critical point, form closed loops. So a magnetic field, let's suppose, comes out of one end of a magnet, loops around like this in the region around the magnet, and comes back in the other end, but it doesn't stop there, it continues through the magnet. Okay, so if this magnetic field represents the orientation or the direction that a compass needle will point, if placed at these various locations, it gives a sense of what will happen if we put a compass needle inside of the magnet somehow. So again, this is an abstract concept of this field surrounding the magnet, and what it tells us is if we were to put a compass needle right there, it would point this way. If we were to put a compass needle there, it would point this way. If we were to put a compass needle here, it would point that way, which is exactly what's happening here. If we were to put a compass needle here, it would point that way. And if we drilled a hole into the magnet and we were to insert a compass needle inside of the magnet, it will point that way. That's what's happening here. Okay, so let me draw a few more of these magnetic field lines to give you a sense of what's happening. I'll draw another magnetic field loop right there. So they're always pointing out of this pole, around like this, to like that. And one can draw literally an infinite number of these, but I'll just draw a few of them. I'll draw another one that kind of comes out of the side, loops around like this. Okay, so that's what the magnetic field lines are going to look like. Again, it's pointing to the right inside of the magnet and to the left outside of the magnet. And notice they don't all come out of the face. Some of them come out of the face, but not all of them. But the important point is they all form closed loops. This is going to be different than when we come across the concept of the electric field. Electric fields need not form closed loops. In fact, they start on positive charges and end on negative charges, whereas magnetic field lines form closed loops. So if you understand this, then it becomes clear what's happening with these compass needles on the outside compared to the inside of this torella. So let me make a sketch of what the magnetic field lines would look like, roughly, in the vicinity of one of these broken torella. Okay, so we have these magnetic field lines that are going around like this. Like I said, one can draw as many of these as you have the patience to do, and as many as the precision with which you're attempting to make your diagram. But you can see what's happening here. Let's draw a couple more. I'm trying to draw closed loops. Okay, so notice here it's pointing outward, around, around, and then on the inside it's pointing to the right, on the outside it's pointing to the left. Right here it's pointing to the right, up here it's pointing to the left. So as these loops, as you draw smaller and smaller kind of fine-grained loops in here, there comes a point where there's sort of a sudden abrupt change from pointing rightward to pointing leftward. And that is exactly what's happening up here. Okay, I hope this gives you a sense of how eventually we're going to make sense of what Gilbert's empirical observations are. Again, Gilbert is not observing magnetic fields. All he's observing is the direction that a versorium or a compass needle will point in the vicinity of a magnet. This is an abstract concept that will be introduced later by Michael Faraday, which will help us to organize our thinking. Okay, why don't we stop there?